Welcome back to the Ephemeris podcast. I'm your host, Feeling, and it has not actually been that long since the last episode because, as I promised, we will be dropping multiple episodes this week, and I'm assuming that this is going up on Wednesday. I will be uploading another episode on Friday, and that'll leave us with just um, one episode to make up. But other than that, I have no other details to mention in the introduction to this podcast. So let's just get into the topic of today's episode, which is Edwin Hubble. Hubble was very influential for his ideas about the expansion of the universe and the existence of other galaxies, which is exactly what we will get into. But first, let's start with some biographical details. Edwin Hubble was born in 1889 in Marshfield, Missouri, and after living there for a year, his family moved to Wheatfield, Illinois. And Hubble happened to be a very, very talented athlete. He participated in baseball, football, basketball, and track, which is a lot of sports. It goes without saying. And Hubble went to the University of Chicago on a scholarship and concentrated on mathematics, philosophy, and of course, astronomy. He got a bachelor's degree in 1910, and Hubble ended up bouncing from college to high school teaching in, I think it was Indiana, before doing his graduate studies at U Chicago, and then the war, or the Great War, World War I happened, and Hubble ended up joining the U.S. Army, and that's different compared to Eddington because Eddington was actually a pacifist, and he was not interested in participating in the war. So there's a slight difference between the two personalities we've talked about in the last two episodes, or this one and the last one, and yeah, some details about that actually. Hubble rise to the major rank in his division, even though I don't think he actually ended up being on the front lines as much. And he ended up in Cambridge after the war. And so, in that sense, Hubble's life did not happen in just one place. He was definitely all over. So, with that all being said, the rest of his career after that was just being at the Mount Wilson Observatory in Pasadena, California for the rest of his life. So let's just have a look at Hubble's PhD dissertation, which he wrote in 1917, which is titled Photographic Investigations of Faint Nebula, to start looking into his work. There are a couple of quotes that illustrate some cool concepts, so let's look into those. First one. Quote, the evidence, while far from conclusive, appears to indicate the existence of actual clusters of these small nebulae in the sky. If this is true, it is natural to suppose them physically connected, as is the case in star clusters. It is not possible to form a conception of this state of affairs until some idea of their distance is acquired. Suppose them to be extra sidereal, and perhaps we see clusters of galaxies. Suppose them within our system, their nature becomes a mystery. So, yeah, this is very early on in the piece where he has looked at, I think, a couple of nebulae from like the New General Catalog, Messier Catalog, some tables of observations that he's retrieved from multiple sources, and he begins to talk about sort of the existence of, let's just call it something else, in the corners of the night sky. You know, he describes it first as clusters of small nebulae. And he considers them physically connected, which is interesting because that could mean multiple things. There are different types of physical connections. There's like, gravitational attraction that happens in globular clusters, but also, the gravity of a black hole at the center of a galaxy, right? So it's not as clear what he's talking about here. Like, it's not a very, very clear indication of, oh, he's talking about, well, these have to be galaxies, but it's definitely heading in that direction. Yeah, and he mentions that if we suppose these sort of systems to be within our galaxy, their nature becomes quite mysterious, and it requires a little bit more investigation. So yeah, that's the first thing. A second thing that comes up is at some point in some theory that Hubble is talking about in the piece, he lays it out by first saying that, quote, assume an axis perpendicular to the line of sight. The mass is concentrated in the nucleus and the individual distant particles as rotating in equilibrium. I believe, I can't remember exactly if he was talking about the same faint nebula as the first quote, but it's interesting to see how these visualizations are hinting at this idea that, there's a concentrated nucleus in the middle of um, a celestial object with a bunch of stuff like rotating around it. And Hubble also makes a mention of Eddington in this very, very long excerpt. Quote, the conception of our galaxy set forth by Eddington in his book Stellar Movements and the Structure of the Universe, which, side note, we studied, is that the Milky Way forms a ring around a central, slightly flattened cluster. This ring is supposed to rotate in equilibrium so that the stars may remain concentrated in the configurations they now form. Assuming the ratio of the two radii as 1 to 5, this is a little bit of numbers, just putting this out there to put this out there, and using Eddington's figures of 2,000 parsecs for the distance of the Milky Way and 109 suns as the mass of the inner cluster, the period and density may be computed and compared with those of the typical nebula placed at a distance such as will make the diameter the same as that of our system. So yeah, after mentioning sort of the uncertainty of whatever these faint nebulae are, he brings in these ideas from Eddington's work and says, if we apply this to sort of these faint nebulae that are distant, maybe we might figure out some similarities that make them other kinds of galaxies that are different from our single system, or we might kind of disprove it if we do not see the similarities. So another thing that he says, quote, considering the problematic nature of the data, and this is after he sort of puts in a table of data about certain nebulae, quote unquote, that he sees in the sky. Considering the problematic nature of the data, the agreement is such as to lend some color to the hypothesis that the spirals are stellar systems at distances to be measured often in millions of light years. So yeah, he sees these spirals as he describes, and he notices that their distances have to be quite far, because even though the nature of the data is problematic, that does still tell us something. Another quote that is brought up in his work, it is suggested that the spirals seem to follow the distribution of the small faint nebulae. If this is true, the most that can be definitely stated is that they tend to cluster in certain regions of the sky. So now we see this idea, okay, we have this table, we have these quote-unquote spirals that we're seeing in the night sky. They're very distant. It can be suggested that these spirals are follow these distribution patterns that kind of connect them with clusters in certain regions of the sky. So it's sort of piecing together, even though I can't really put together all 16 pages of the work for you to understand it simply. But the way that these quotes progress, they show you that, okay, we have this observation of faint nebulae. It's possible that they're in a different system. There are observations of spirals that may be connected to certain clusters, and sort of this progression of this whole other galaxy idea will come to fruition. So yeah, that is pretty much all of the quotes that are getting to this idea. And then in 1923 and 1924, Hubble began to investigate the Andromeda Nebula, as it was called at the time, and made some key discoveries. He was using the Hooker telescope, which is a very, very good telescope at the time, at Mount Wilson, and he sought to figure out the distance between us and the Andromeda Nebula, right? How do you do that? Well, as we established in a previous episode, Henrietta Leavitt discovered a law which could calculate distances for Cepheid variables using its luminosity. So that comes in very, very handy here. Because that law has already been, figured out meticulously, it was simply a matter of Hubble finding Cepheid variables in Andromeda to figure out its distance from us. And once he did, there was an obvious realization to be made. That is, Andromeda can't be in our galaxy. It's simply too far. Now, at the time that he did his calculations, his estimate for the distance of the Andromeda galaxy was close to 1,000,000 light years away. Today, we put it at a much larger distance. I think it's 2.7 something million. But, I think across his PhD dissertation and probably some of his other works, he will admit that there is a lot of room for error in the calculations that he does. But, so the general idea is just that finding this galaxy that is way too distant, and now you understand, okay, well, we can't be the only galaxy. There's got to be another galaxy that's out there that's way distant from us, that's holding on to a bunch of stars that are outside of our system. And that kind of opens the floodgates to a larger universe, or the conception of it. After this discovery, Hubble created a classification system for galaxies known as the Hubble sequence in 1926. And the diagram shows that, the diagram that shows the system resembles a tuning fork and contains three broad categories of galaxies: spiral, barred spiral, and elliptical. So to expand on that briefly, spiral and elliptical galaxies would look exactly how they sound, spirals with a bunch of arms surrounding the center, elliptical galaxies being in the shape of an ellipse, and bar spiral galaxies are basically you have two bars, hence the name, that are extending out from the center, and then they turn into a bunch of spirals. There are a couple other types that either don't get much recognition in the diagram itself, or just don't exist on the diagram at all. And one of them is irregular galaxies, which don't have a defined shape. And then there is lenticular galaxies, which is kind of like this midpoint between the tuning fork in the diagram. It's not labeled that way, I don't think. But essentially what lenticular galaxies are, they're intermediate galaxy between an elliptical and a spiral galaxy, and they have a bulge in the middle, and then they have a disk around that bulge. So we can take this information for granted today. It's very easy for me to just say, oh, here's the sequence, these are the galaxies, this is what they look like, this is the evolution. But to understand it in the context of Edwin Hubble discovering it, it's very important, because at the time, lenticular galaxies were purely hypothetical, and all of the stuff that he talked about in his PhD dissertation that hinted towards the idea of distant galaxies was very, very contentious. And some astronomers that figured out his work in 1925, when it got published it got sort of given to the Royal Astronomical Society, some of the astronomers are scoffing at it, because they didn't believe in such a thing, or they didn't believe in the discoveries of Hubble and all of this classification of galaxies and things other than the Milky Way existing. So that's that for 1924 and before that. In 1929, Hubble conducted research on the radial velocity, distances, and redshifts of galaxies that was, to say the least, out of this world, and quite literally. He discovered that the distance of between galaxies is proportional to the radial velocities of the galaxies, or in layman terminology, the farther away an object is from us, the faster it travels away from us. And in building on this idea, the Hubble constant arose, which is a constant of proportionality that equates the separation velocity of one galaxy from another to its proper distance. So, the typical analogy that is used with the Hubble distance, or Hubble constant and distance equating to velocity, is kind of like raisin rising in a bread. Like if there's a raisin at the center of the bread and it's 5 centimeters from the and there's a raisin that's 5 centimeters from it, when that bread expands, the 5 centimeter difference just kind of increases by a factor, and then the distance between those two is kind of proportional to the rate at which they are separating. And so that's kind of an analogy to help you imagine what the Hubble constant is doing in the context of, separation velocity and proper distance. So the Hubble constant also uncovers the expansion rate of the universe, and I think that one takes a little bit more tedious calculation, but there's a rate that comes out of it. I think it's about like 7%. I don't remember what it is. And fascinatingly, this is another thing about the Hubble constant. Its inverse is actually Hubble time, and that and the reason why it's Hubble time is because Hubble's constant is actually a frequency when you FOIL out the units, which is very interesting. So when you flip a frequency, which is an inverse second, you get a second. So the inverse of Hubble's constant ends up being Hubble time. And there were a couple of people who figured out these ideas a little bit before Hubble. I believe I think his name is Alexander Friedman, and then there's another French guy who shares the name of Hubble's law, but I don't remember how to say his name. And yeah, I mean, that's pretty much all I had to say about Hubble's law. And in 1936, Hubble published The Realm of the Nebulae, a historical and explanatory piece on his research in the field of extragalactic astronomy. So, yeah, that is pretty much all there is for Hubble's work, and that is where I'm going to wrap up the episode. If you guys enjoyed listening to this episode, I would sincerely appreciate a follow on Spotify if you're listening on Spotify, and a subscribe on YouTube if you're listening on YouTube. And until the next episode, I will see you all later. Peace.